Hello, and welcome to part 3 for my progress check for pre-calculus, Unit 1, Topic 3, Formative Assessment 1. In this video, we're going to be talking about rational functions, and more specifically, calculators will be available, which is going to be really super nice. And what I'll actually end up doing here is I'll be incorporating the program Desmos to kind of help us along with these types of things. Now it says you may use the grid to help you. I might actually end up using it. I might not. I am not sure, depending on whatever values that I get from this. So the first thing it says is it says describe the indicated properties of the rational function g. You may use the grid to help you along. So it says x and y coordinates of a hole. So already right off the bat, they're going to tell you that there is going to be a hole for this problem. And one of the kind of bad things when it comes to modern day technology, especially for the TI-83 and 84 calculators, is they do not show a hole when it is actually there. They show it in a table, but they will not show it actually in the graph itself, right? It's just kind of part of how the technology ends up working out. So one of the things that I see from this graph, they already actually reduced it for us, which is fantastic. That kind of cuts down on some time. So I take a look at the x plus 3 squared over x plus 3 and x plus 2. And most of you guys are probably going to see that, okay, the x plus 3, and then one of those can cancel. So I'm actually left with x plus 3 over x plus 1. So what that means here is a couple things. That means that at x equals -3. So that means that the value, in a sense, that gives me 0 for this problem, that means that there is actually going to be a hole at x is equal to -3. So when I cancel that out. So that there's going to be a hole. But where is that hole going to be? Well, what ends up happening is if you take that -3 and plug it into the canceled version, so I'm going to write parentheses plus 3 over parentheses plus 1. So I'm taking this factored version and I'm plugging in this -3. So what ends up happening here is I end up getting 0 over -2, which actually gives me 0. So that means at the order pair, -3 comma 0, there's actually going to be a hole. So that's what I'll actually end up putting in here. At -3, 0, that means there's a hole. A couple of other things. Now, if I looked at this problem originally from the very beginning, it would look like that I would have an asymptote at x is equal to -1 and also -3. But since there was some reduction, right, I could cancel some values, there is actually not a vertical asymptote at -3, but more specifically a hole, which I figured out. Now, since there was no cancellation at x is equal to -1, that is going to be my vertical asymptote. So we do have a vertical asymptote at -1. So I'm going to place in my asymptote at -1. I also notice that I have a horizontal asymptote. I look at specifically the highest powers. So if they end up having the same high exponent on both the numerator and denominator, then I know that this is considered to be called equal heavy. And when it's equal heavy, I take a look at the leading coefficients of the highest exponent. So in this case, I notice that that's a 1. I notice that that's a 1. So my horizontal asymptote is actually going to be 1 over 1, right? We take those specific numbers. So if it was like, let's say 2x squared over x squared, that would be actually just y is equal to 2 over 1. But in this case, it's going to just be 1, so y is equal to 1, which is going to be my horizontal asymptote. Now, that does not necessarily mean that the graph can't intersect the horizontal asymptote. The horizontal asymptote really just means that we're talking about the end behavior for this graph. So what I'll do here is I'll actually show you what this graph looks like in a graphing utility. So I'll write y equals, this is going to be division bar x squared plus 6x plus 9, and then over x squared plus 4x plus 3. And so we end up getting a graph that looks like this. And right here, actually at -3, we can see that there's actually going to be a hole. So if I really wanted to graph this, there are some other points here. I noticed I have 0, 3. So at that point, and I know the graph hugs it from there, hugs it there. Same thing right here. Right, that point is just kind of used as a guideline. And there's my graph. Sorry, I currently have a cold at the moment. Accurately graph the rational function h on the grid, including any asymptotes and any dashed lines. So what ends up happening here is I'm looking at both the reduced version and both both parts of the graph. So what ends up happening here is I look to see the x minus 2, right? There is no reduction in terms of I can't cancel an x minus 2, so I know my vertical asymptote here is actually going to be x is equal to 2. It is technically whatever value that sets the denominator equal to 0 that I can't actually have, right? And so if I plug in 2, I get 2 minus 2 for the denominator, so it gives me 0. That's a no-go. So I'm going to place in a vertical asymptote at 2. The next thing I'm going to notice right here, when I set the top equal to 0, these are called my zeros. So those values are going to be 0 and 1. So that means I have a point at 0, 0, and also 1, 0. Oop, and at 1, 0. Now that looks kind of odd, especially for what this graph is going to look like in the end, but I do have those two values, just kind of how it's made up. Now my horizontal asymptote is I look at the top heavy, bottom heavy, equal heavy attributes to the problem, and I can see that we have an x squared at the very top. So what that means is that this is top heavy. So that means that there is no horizontal asymptote, which is fantastic. But what that also really means here is that we actually have to figure out whether being a slant asymptote. So to figure out whether it is a slant to figure out what the slant asymptote is, we're going to have to do some good old long division. Now you can use synthetic division if you feel more comfortable. Me personally, I kind of like doing long division. It seems to work out nicely, and you don't have to worry about any of the special cases that are tied with synthetic division. So I'm going to write x squared minus x inside, and then x minus 2 is on the bottom, or x minus 2, which is on the bottom, so that's going to be outside. The next thing I do is I focus on the x and I focus on the x squared. So I say what times x gives me x squared? And in this case, that's going to be x. So x times x, that's going to give me x squared, minus 2x, right? Because I still have to do x times negative 2. The next thing I'm going to do is I'm going to subtract those values. So I want to say x squared minus x squared, those two are going to cancel. I want to say x minus negative 2x, which is actually in another way of saying plus 2x. So that's actually going to give me positive x. What times x gives me x? Well, that would just be 1. So that would be x minus 2 in a group of parentheses. Subtract. Those two are going to cancel, but that's going to change the minus 2 to be plus 2. And that's technically going to be my remainder. So I'm going to say x plus 1 plus 2 over x minus 2. So that is doing long division, breaking down this actual graph. So my answer here is actually going to be this x plus 1. So this is my slanted asymptote. So I'm going to say slanted asymptote, SA. That's going to be y is equal to x plus 1. So I'm going to graph this in a little bit of a different color. So I'm going to graph it. I know that I have a y-intercept of 1, so I'm going to place a value at 1. Okay, you can move out of here. I'm going to place kind of like a lighter value at 1. And then I know I go up 1 over 1. Up 1 over 1, up 1 over 1, up 1 over 1. Keep going. And then what I'm going to do here is then I'm going to just kind of do a dotted line. That's going to stand for that problem. Now, what ends up happening here is that we end up getting some type of graph. So it says, accurately graph the rational function h on the grid. So I'm going to try and do the best that I can, right? There's never going to be anything perfect for this. You can also do this. So I'm going to go over to my graph, and I'm going to graph this. See if I can maybe get some ordered pairs to kind of help me along with this. So I'm going to write the following. Where am I? So this is going to be y equals division bar x squared minus x over x minus 2. And in your case, you might be able to just kind of look at your table and get some x value. So we can see that we have a value at 0, 0, 1, 0, and then some type of decimal right there. So I'm going to try graphing that really quickly. So it looks like that it's going to be leaning more towards kind of towards the 1, but it still ends up having a graph that kind of curves to the asymptotes. So something like that looks like that. And then looking at my other side of the graph, if there's any types of values that look like I can get. So it looks like that there's 3, 6. So it looks like I have a 3, 6. It looks like I also have a 4, 6 as well. And then it kind of dips down below there too. So I end up getting something that looks like this. And there's my graph. Now I don't need a bazillion points for this, but I just kind of need to get the gist of the lines and then also make sure that I put in the asymptotes as accordingly. Oh, and also remember my arrowheads. Okay, moving on. Okay, it says describe the indicated properties of the rational function f. You may use the grid to help you. So, yet again, awesome that they end up reducing it for you. So my zeros here, right, those are the values that are when the top is equal to 0. So we're going to say x is equal to -1. So that means at -1, I have the point -1, 0. A couple of other things. I know that I have a vertical asymptote at x is equal to -4 and x is equal to 3. So I have a vertical asymptote at x is equal to -4 and also at x is equal to 3. So at -4, dotted line, at x is equal to 3, dotted line. Okay, so they talk about as x goes to negative infinity, as x goes to positive infinity. I'm going to just have this part of the graph here. I'm not going to actually fill it out because they don't even ask us to do it. So guess what I'm not going to do? I'm not going to do it. But in the meantime, what I can do here is I can actually take a look at my graph and use my own graphing utility, get some type of understanding of this graph. So let's clear out the other one. Y equals division bar, x plus 1, and then over, and you can do the reduced version. I'll actually do that. So I'll write x plus 4, x plus 4, and then another x minus 3. Okay, so we end up getting a graph that looks like this. So that's kind of interesting. So when it says as x goes to negative infinity, so we can see as x goes to negative infinity, right, we see that the value actually gets closer and closer to 0. So that will be 0. Also, that's also referring to the horizontal asymptote for this. And if this is bottom heavy, which means that the exponent here is the highest, if it is bottom heavy, it is going to be y is equal to 0. As x goes to positive infinity, that is also 0 from this side, right? It's getting closer and closer to 0. Even though it technically hits 0 right at this point, right at that point. But that's not what we're referring to. We're only referring to the ends of the actual graph, or also known as the end behavior. Now, at -4, so we're taking a look at -4 right here, we can see that on the left hand, or excuse me, this is the right hand side, where we can see that it is going up to, in a sense, positive infinity, right? It keeps going up to positive infinity. So here is going to be positive infinity. On this side of the graph, it is going, well, we're talking also about now positive 3. Okay, so positive 3 right here. We're looking at it from the left-hand side. This is going down, 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 down. So down to negative infinity, so that's going to be negative infinity. So this is supposed to be positive infinity, and the other one is supposed to be negative infinity. Okay, and I think that is it. If you like this video, please comment down below that you enjoyed it, or if you have any types of questions, feel free to comment down below, and if I'm available, I'll be more than happy to help you. But other than that, thank you for watching, and have a good day.